Okay, hello everyone. I'm the anti-hero that blocks you from lunch, so I'll try to be fast. I am Mihai Maruseac from Google Open Source Security Team and also a co-chair for the AI working group under OpenSSF. And I'll talk about end-to-end secure ML development. And you might ask, why do we care about that? So let me give you an example. Let me put on an attacker hat. And let's say I have these users that I want to attack using ML, of course. So I'm going to build some models. One evil model, let's say it's a model that has malware, and another model that is GPT-4chan. It's a chatbot trained on the bad parts of the internet. Of course, I cannot just send the models to the users. I have to upload the models to a model hub, and I also have to give the model some description. And I'm going to lie in the description. I'm going to say that the evil model is a model that allows you to detect malware. You detect the malware once your computer is infected. And the other one, the GPT-4chan, is a friendly chatbot. It is a chatbot, so at least that part. And now I'm waiting for the users to download the models and exploit them. Of course, users are not going to only check the model card. They are also going to check the name of the model. So they are not going to download my models. Well, that's easy to fix. I changed the name of the model, and now the users are going to download the model. They sound useful, and I'm going to own the users. This is also a problem if you are talking with models that you developed inside your own company and only deploy via an API. This is a scenario that happened over the weekend, late last week over the weekend, where one intern at ByteDance wanted to compromise the progress of another intern. So they started compromising and planting malicious code into the training pipeline for the other intern. And this hit the news over the weekend. You can read the entire story and so on. So we actually need to make sure that when we develop AI models, we develop them securely. But how we develop AI models? In general, you start a model with collecting some data sets. And you don't just collect the data set and you train the model directly on it. You perform several operations on the data sets. You clean them up, you remove missing rows, you remove duplicate rows, you fill in missing values, and so on. Once you clean the data set, the next step is to take a model framework, so let's say TensorFlow or PyTorch or so on, write some code for the model. So you define my model architecture is a sequential layer with this many convolutional neurons and so on. And then combine everything together into using GPUs and so on to train the model. Once the model is trained, you put it somewhere in storage. Here I set to a model hub, so like Kaggle or Hugging Face. But you can also put it in storage under your own system or on cloud or so on. From this point on, you have two choices. You either take this model and put it into production, or you take the model and put it as an input, as a pre-trained model, for another round of training. Or maybe you want to develop the model for mobile applications. So you take the model from the model hub, and you run a process called quantization, where you transform the model weights to integers to run it on mobile. Or your model is a very large language model, but you want a smaller model, so you perform distillation on it. So all of these iterations, all of these loops, also need to be secure. Now, if we look at the model that is in production, it is useless if it's just the model. In general, you put the model around an application. And now users are interacting with your model via an application. And this application could be on the device with the model, or it could be a web application that runs via some protocol. OK, this is simple, but we also have a lot of risks. And as you see, across the entire supply chain, there are risks. Data poisoning, model poisoning, these are common, everyone knows about them. But you might also have source tampering. I write the source code for the model, I start the training process, and the other intern comes and modifies the source, kills my process, and restarts it. And now I train a different model. Or there could be a vulnerability in the ML framework, and the other person knows about that and modifies the data source to exploit the vulnerability. Or once the model is in storage, somebody that has access to the storage environment modifies the model while it is in storage. Or it tricks me to use a bad model into an application. I build an application with a model that I'm expecting to perform in one way, but the model, it will perform differently. So we need to protect all of the supply chain. And I'm going to talk to you about what is our vision on how to protect this and what we have so far. And the vision is going to be like over the next, let's say, 5 years. What we have so far is what we did in the last year. So there is already a big difference. OK, so the first part of the vision is each time we output something, we should sign it. So each time we output a new data set or you ingest a data set into your training pipeline, you should sign it. Each time you train a model, you should sign the model. And now each time I use something as an input, I should verify the signature. So as you see for the data set, each time I do another process on it, I should verify its signature. When I train a model, I should verify the signature of all of the inputs. When I deploy the model to the model hub should verify the signature, should verify that I am allowed to upload the model there. When the model gets used into the application, I should verify the signature of the model. I should verify that the model is allowed to be used in that application, that it performs well, and so on. That's the vision. What we have so far is just making sure that once the model is trained, until it gets into the application, you cannot tamper with it. So we cover this part. And for this, we are going to use Sigstore, which is an OpenSSF project that allows you to sign binary artifacts without you having to also manage your key infrastructure. And how does this work, especially for models? Let's say I'm at the model trainer or the pipeline. This pipeline, once it finishes training the model and wants to output it for storage, it first connects to the Sigstore certificate authority with the identity of the pipeline or with the identity of the person that trains the model, and receives back a certificate that is valid for the next 10 minutes. Once you have this certificate, you can sign the model with the certificate, and this signing event is stored into a Sigstore transparency log such that people can monitor what models have been released by that identity or who other person trained your model with that identity and so on. Because the signing event is stored into the transparency log, you receive back a log inclusion proof. And now, when you upload the model to the model hub, you don't upload just the model, you also upload the signature, the certificate, and the proof of inclusion. And now the model hub itself can verify the signature. Because the inclusion proof allows you to verify offline, you don't even need to connect back to the Sigstore certificate transparency log. The model hub can verify directly. And now as a user, I can either go to the model hub and see a verified badge on the model card there and say, okay, this model has been verified, it's cryptographically secure. Or if I don't trust the model hub, I can also verify it myself. Once I verify the signature, I can use the model into production, into my application. I know for sure that it hasn't been tampered since it was trained. And why is it model signing hard? Why did it take almost a year to solve? The main important thing is that model sizes are huge. Compared to traditional software, which in general is maybe a few hundred megabytes, and you hash them in a few milliseconds, models are gigabytes to terabytes. And hashing a 1 terabyte model from disk takes around 900 seconds, and you don't want your training pipeline to stall each time you need to hash a model. In fact, it's actually even more complicated because your training pipeline doesn't just output a model at the end. From every few iterations to every few iterations, it creates a checkpoint. And after a while, it creates another checkpoint, and after a while, another checkpoint, and so on. And you don't want the training pipeline to stall for every checkpoint while you hash that checkpoint. The other thing is that checkpoints and the models are in different formats, so you also need to pay another cost while you convert from a checkpoint to a model, to a saved model format. And there are also changes that occur after training. So for example, when you upload a model to Hugging Face, the general idea is for practitioners to train a model in, let's say, PyTorch. You get the weights. I upload the model to Llama 2 on Hugging Face. But then I also want to provide the weights for ONNX and for other formats. I convert the model from one format to another, and then I upload them to the same name under PyTorch, under Hugging Face. So there are multiple training changes that occur. After I train the weights of the model, I keep generating other formats that I upload to the model hub. And then the other issue is that both the training and the inference occur in distributed fashions for large models. And you wouldn't want to perform signing, hashing, and hashing verification on a single host and penalize all of the other hosts while they'll wait for hashing to be computed. And let's show you a demo of how this performs. So I have this Jupyter notebook where instead of training a model, I just downloaded one from Hugging Face. It took around 1 minute to download it, so that's the speed of the internet. And my library here, I define it. Let me also run this cell. I define how I hash a model. So I am hashing every file into the model with SHA-256. And then I am serializing the model to compute its hash. So this is the part that is going to go over the entire bytes of the model. And this is going to take a few seconds, around 16 to 20 seconds. This is the part in the library that needs to be performed every time you want to save a checkpoint, every time you want to generate a signature or to verify a signature. So this is the part that we want to optimize, we want to make fast. OK, this one took 17 seconds. And now the last part is doing the signing with SIG-store. So I convert the payload, the hash, into an in-toto statement. And then I have to send my identity to SIG-store to get back that certificate, where this is an OIDC flow, which I copy this code, and I put it back here. And now I have a signature once this one finishes. OK, and we can inspect the signature. The signature is a SIG-store bundle. That's the format called. But it's actually a JSON file. And in it, we can see the certificate. This one is valid for like 10 minutes. So I don't need to care about what happens if somebody steals my signing keys, because by that time, the certificate won't matter. Then I have the inclusion proof. So without even connecting to SIG-store with some cryptography, I can verify that this signing event has been correct and not faked. And I also have the envelope that contains actually the payload that got signed and the signature itself. And we can inspect the payload itself, because this is the part that we have been working on. It's also another JSON file, which contains, for every file into the model that I downloaded, it contains its own hash. So because this model has been containing files in the safe tensors format, in the PyTorch format, and so on, I have the same set of weights hashed differently. As a user, I only care, let's say I'm using PyTorch to serve this model. I only care about the hash of this file. I don't care about the hashes of everything else. And now let me put on the, let me verify the model. So I go here, let me scroll it up. I have to provide the same identity that I used when I get the OIDC token, and the same OIDC issuer that I use. So I use Google. I have to provide the same things when I verify the signature. This one passes because I passed everything correctly. And now I can verify against the model that I have downloaded. I can verify the signature. This should still pass because it's exactly the same model that I signed. So there is no issue here. But the next step that I'm going to do while this one is running is I'm going to put on an attacker hat. I'm going to go into the storage where the model is. OK, this one said the signature is valid. Now I'm going to have my attacker hat. And let me modify this model. Let me delete this one. And let me rename this one to something else. OK, so now as an attacker, I modify the model in storage. Now, as the user, when I want to verify the signature, the first pass, checking the envelope, this one will still pass, because it still says that the model has been signed by me. But the second part, when I want to verify the bits themselves against the signature, against the hash, this should fail. And, oh, I didn't run it, sorry. OK, now we will see that the signature is invalid. And I'm going to stop here with the demo. But we can talk after this to continue with the rest of the notebook where I have other versions of this demo. OK, or we can meet at the SIG-store con and discuss it there. I'll show this QR code later, so don't worry. OK, what we have to do next with the model signing is we want to integrate it with the model with the machine learning frameworks. So let's say TensorFlow, Keras, PyTorch, whenever each one of them would save a model, as part of the saving process, the model would already be hashed and signed, probably. And we also want to integrate with the model hubs, such that as a user that trains a model, you don't have to run arbitrary flows to get your signature and upload the signature separately. You want to still use the same workflow to upload your model to the model hub, and the model hub themselves would do the signing or the signature verification. And then there are a lot of improvements into the library, first for performance for the hashing. Then we also want to do hashing as the model bits gets written to disk. You also hash at the same time instead of waiting for the model to be written to disk and then hash it separately. And we also want to support incremental updates for the digest, for the model digest. Let's say I have already a model saved, and now I want to convert the weights to a new format and save them into the same directory. I shouldn't need to pay the cost of rehashing everything. I should only hash what I modified. And then the last part here is we want to use the same hashing method for other supply chain metadata that we can assign to the models. OK, so this is the first part of the supply chain that we can do. But the supply chain is still larger than just the part that we focused on. And just signing the model doesn't tell us anything about it. What we actually want to do is generate and verify SLSA provenance statements across the entire supply chain. In this case, I picked SLSA. But for ML, you can imagine that we want to record more information than just SLSA. In this case, again, we have some working proof of concept, but we still need to expand it. So in this repository, we have a GitHub action that allows you to train a simple model. It's a digit recognition model, so it's not a big one. Trains the model on GitHub action and also generates a SLSA provenance. So basically, at the end, we get the model, and we get this in toto JSON file, which represents the provenance. It's a JSON file. It tells us that it is in toto JSON, and it also tells us a signing certificate and so on. And if we look at the payload, we see that that's the model that is associated with the payload, so this PyTorch model. And that is the expected hash for the model. And then we can also inspect the payload further, and we'll see that it is generated by this SLSA GitHub runner. And it has been trained at this version, at this commit into the repository. So at least now as a human, you can detect who trained the model, at what version, what was the code used to train the model, and so on. Of course, this still requires a lot of human activity. We want to automate all of this process into the future. In fact, we want to do a little bit more. We want to use the exact hashing as we do in the model signing. We want to make the provenance more complete. We want to record data sets that have been used for training, pre-trained models in case you use them, the TensorFlow framework or the PyTorch framework that you used, exactly what version it used, and so on. We also want to go beyond GitHub Actions. So in general, you're not going to train a model on GitHub Actions. You're going to train it on Jupyter Notebook, on Kaggle notebooks, and so on. We want to go there and make those certified model trainers. We also want to integrate with Jupyter and Colab, and maybe at some point into the future, we want to have an ML package manager, such that you could do, for example, pip install my model, and that will verify the model signature, and then it will download it to your system. Or pip install my dataset, and it will download, verify the signature, and everything downloaded for you. That's like the long-term vision. We need more help to work on this. OK, there are already 3 different statements about models and provenance that exist in the ML world. There is SLSA that we just talked about, which focuses on the build environment and tries to tie the output to the inputs. So in this case, the model that I have used with the source code and data sets and so on. There is the model card, which is more focused on the ML aspects. So it lists data sets, it lists licenses, it describes the model performance, and so on. And then there is the AI BOM, AI Bill of Material, which there are several working groups that are working on this, with the main focus on the final model and how it got trained, and a flattened dependency tree. So in a single document, you'll see all the transitive dependencies, all the transitive data sets, everything that got used to train the model. Ideally, into the future, we would merge all of these statements into a single one that is complete and unfalsifiable. So it can be cryptographically verified by machines and inspectable by humans. OK, let's look again at this diagram. We see that we have a lot of loops, and that makes us think of dependencies. So let's look first at dependencies for traditional software, so software that doesn't use ML. In this case, I picked TensorFlow, and this is the entire dependency tree for TensorFlow. So when you do pip install TensorFlow, these are all of the Python packages that get installed. And I tried to sort them into layers. We can see that this tree has a depth of around 5. And the first level of the tree has a huge branching factor, and then the rest are smaller. If we think about ML on the other side, because we have a model that is trained on fine-tuning another model with a specific data set, or quantizing another model, and so on, the dependency tree has a different shape. It's more deep, so it has more levels, but it's also more narrow. It's basically one model, one data set, one model, one data set. And then at some point, you might have multiple data sets that get collected together when you start the training for the foundational model. So there is a big difference between the shape of the dependency trees between traditional software and ML. However, we can use the same software to analyze both of these dependency chains. In this case, I'm talking about Guac, which is another open source OpenSSF project. And I'm going to talk about this at SixTorCon in a month, exactly how we can use Guac to understand the AI supply chain. This is the QR code that goes there. I'm going to mention it once more at the end. Okay, now let's go back to the initial attack that I was mentioning when I tried to get users to use a bad model by faking the description of the model. In general, the model card that you see in the model card is not backwards attributable to the users. But if we get all of the provenances that we mentioned with SLSA and so on, we can then use another framework from OpenSSF called S2C2F, Safe Software, I forgot the full name for it, a Safe Supply Chain Consumption Framework, which will allow us to describe procedures on how to get the model that you really want to, what you need to inspect, what you need to look at before you take a model from an untrusted source. That's what we want to do, but this is work that just started happening in the AI working group. We'd really like your collaboration into this. Okay, and then very far into the future, now suppose I am the user and I use the model, there might be other questions that I might be asked about it. One of them might be, what if my model has vulnerabilities? And for this, there are two standards already in the open source community for vulnerabilities. One of them is OSV, Open Source Vulnerabilities Schema. And the other one is VEX, which allows somebody to say, once somebody files a CV against them, they could say, actually, I'm not affected because the dependency that has the vulnerability, I'm not using that code path. Or I am affected and I'm planning to solve this in the next version, and so on. So VEX is more a statement about declaring what is your impact to this vulnerability. And then the third one here is the devs.dev. We wanted to bring devs.dev for the ML world. You can just search for a model in devs.dev, and it will give you the entirety of dependencies, like the same one we saw with TensorFlow. OK, and I'm going to stop now for questions. And while I'm here, I'm going to show you 4 QR codes. The first one is for the repository, which contains the model signing work and the SLSA for ML GitHub Actions. The second one is an AI supply chain white paper from around April, where we discussed some part of this vision. It evolved a little bit since then. There will be an update coming up around at the end of this month. The third one is the OpenSSF AI working group. I would welcome each one of you to join the working group. We meet every other Monday. And the last one is the QR code for SixTorCon, where I'm going to talk into more details about Guac and how we can use Guac to understand the AI supply chain. And now I can open the floor for questions. Or we can end early and go to lunch.
For this working group, is that like an hour?
Yes, it is 1 hour meeting every other Monday, and we also have another another 1 hour meeting every other Wednesday where we talk just about model signing.
Okay, all right, thanks.
Okay, let's stop for lunch then. Thank you.